Assalamualaikum and very good day to all students taking this course. Today we are going to venture into chapter 1, which is quite an introduction chapter regarding the organic structure and bonding. I am Associate Professor Dr. Najrul Hashrabi Manayan. I'm going to be your lecturer for this course. So today we are going to venture into chapter 1, part 1. Okay, for chapter 1. The structure determines the properties of atoms, electrons, and orbitals. So molecules are made up of atoms. Atom we have a proton, positive charge, and negative charge masses according to 1.6726 multiplied to the power of negative 27 per kilogram. Okay, whereas neutron have no charges. Its mass consists of 1.6750 to the power of minus 27 kg, and whereas electrons carry the negative charge having a mass of 9.1096 to the power of minus 31 kilogram. Okay, the atomic number which is being represented by the symbol Z is the number of proton in the nucleus. Okay, so the nucleus is equivalent to the proton and neutron, which is very little volume but consists most of the mass. The atomic mass unit or AMU is equal to 1 divided by 12 mass of carbon 12. Okay. Whereas the electron which circulate about the nucleus, which is negligible in mass, but the electron cloud is most of the volume of an atom itself. For the quantum mechanics, electrons have properties of both of a particle and energy. Energy of an electron is given by a wave function, so the electron have a series of discrete levels. Schrödinger wave equation give you total energy of an electron at a given point in space x axis of x, y, and z. So the Schrödinger wave equation is equal to probability of finding an electron at a given point in space. So orbital is equivalent to the space where an electron spends 95% of its time. The atomic orbital or AOS, it is the electrons are arranged in a shell at a various distance from the nucleus, whereas the shell are arranged in an increasing energy. So within each cell, electrons are paired into the orbital, okay, with each orbital holding 2 electrons. Okay, so the pair electron within an orbital have opposite spin, which is called Pauli exclusion principle. So the periodic charge is organized according to the electron shell and the atomic orbital itself here. So it's organized according to the periodic table and atomic orbital. Okay, so please review and understand the electronic configuration. Okay, in this case, you need to understand the regarding the above principle, Pauli exclusion principle, and Hahn rules. Type of atomic orbital. We have 1, 3, and 5. For the 1 it consists of s orbital spherical, which is represented by these symbols, while 3 consists of p orbital. It's being arranged in a diamond shell shape, where the 5 consists of d orbital, floor cover leaf, and 1 dumbbell with a rings. Okay, whereas for the 7th type of it consists of f orbital. So this here show you how the orbitals are being arranged, and you can see here with increasing the shell that orbiting the atom. You can see here the energy is increasing. Okay, you can see here the 3D, 3P, 3S, 2P, 2S, and 1S. How the orbital is rearranged to circulate the atom. Okay, for the S first K shell, it consists of one S orbital. The second L shell, it consists of 2s orbital and 3p orbital. So you must remember about this. For the 1s orbital, there are no knots here. Okay, you can see here. For the 2s orbital, it consists of one knot, and p orbital it consists also one knot. The 2s here you can see here, 1s orbital. Okay, this is y, z, x, and z, y, x, and z. Okay, so notes the space. Notes is actually representing the space or the point plane surface where the orbitals are being arranged. Okay, valence electron is actually the electron in the outermost shell valence electron that are involved in the bonding. Regarding the octet rule, atom will give up or accept or share electron in order to achieve a noble gas, which is a stagnant state in electronic configuration. Chapter 1.2, subtopic ionic bond. So the electric attraction between oppositely charged ion. You can see here cation that carry a positively charged ion and an ion that carry negatively charged ion. You can see here the natrium here, sodium here. You can see the sodium here is carrying the positive charged ion representing the cation. So here we have the chlorine here. Okay, which and being added with the electron here. So chlorine the carrying the negatively charged ion. So it's one as an ion. So chlorine, since chlorine negatively charged ion, it will combine together with sodium to produce sodium chloride that carry the positive and negative charge, and ion and cation. The electrostatic attraction between oppositely charged ion. Covalent bond. Okay, Lewis structure and the octet rule. Covalent bond result from two atoms sharing a pair of electrons in order to achieve a noble gas configuration. For the 1s orbital, each H of H2 has the electron configuration of He, closed and filled with valence electron. You can see here. Okay, and the energy is about minus 434 kilojoule per mole. Okay, so each atom of ferrum here, you can see is carry 8 valence electron, and the atom configuration of n is in here. You can see here when the C of CH4 has the electron configuration of Ne, while the H have the electron configuration of H electron. You can see it being combined together to produce this molecule. Double bond and triple bond, subtopic 1.4. Okay, you can see here this example of double bond and triple bond is presented by C2H6 for ethane and C2H4 ethylene, how it's being arranged together, how being attracted together to achieve the octet rule or octet configuration. For the acetylene C2H2, how you can see how the molecule, the atom is being combined to produce molecule of acetylene. Subtopic 1.6, the shape of some simple molecules. Molecules are not flat. They are three dimensional. They have x, y, and z axis. Okay, so the valence shell electron pair repulsion, or VESPP molecule, will adopt a three-dimensional chromatography so that the electron pair either in bond or non-bonding pair are as far away from one another as possible. So it will have the tendency to become distant from each other as much as possible. Okay, atom, which is a number of substituent or non-bonding electron pair, is 4. It will adopt a tetrahedral geometry in this. So, an example of methane. 3. it will adopt a trigonal planar geometry. Example of ethylene. 2, it will adopt a linear geometry. So in this case, example of this type of electron pair is acetylene. Subtopic 1.5, polar covalent bond. Covalent bond in which the electrons are not equally shared between the two electrons. Okay, so there is a net dipole between the two atoms. Okay, you can see here example of covalent bond, symmetrical covalent bond. It will look like this. Okay, polar covalent bond is has a tendency to follow the polar covalent bond, and then we have ionic bond. Each atom carrying different charges, making them attract to opposite different charges. Okay, so electronegativity is this intrinsic ability of an atom to attract electron. So in general, the greater the electronegativity difference between the two bonded atoms, the more polar the bond. Electronegativity tend to decrease down a period and increase across a row from left to the right. You can see here. So subtopic 1.10, molar dipole moment. So dipole moment, okay, is a molecule property in which the vector sum of all individual bond dipoles. Okay, you can see here this is dipole moment, okay, representing the charge here and d is the distance. So the dipole moment is the charge multiplied by the distance. The unit is d by, okay. Inductive effects. Atom or group of atom ability to polarize a bond through electronegativity difference is known as inductive effect. Okay, subtopic 1.6, the structural formula of organic compound. So hopefully you can read, understand and practice this. Okay, so writing, drawing chemical structure. A line between two atoms represent a bond. So you can see here a line between two atoms here representing the bond. Okay, so you can see here the example of chemical structure drawing. The first one is calculate, the second one is condensed, another one is skeletal. Okay, the skeletal is a bond line notation. You can see here it consists of bond that represent line that representing the bond. Okay, the carbon atom are the end of the line. You can see here the carbon atom are the end of the line. C, 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 C. You can see here the carbon atom is at the end of the line. Okay, so the hydrogen atom and carbon are not shown. So the hydrogen is not shown. Okay, all non-carbon and non-hydrogen atom heteroatom are shown. So uh, others atom except carbon and hydrogen are shown in the skeletal notation. Okay, hydrogen and on heteroatom are shown. However, in case if the hydrogen are on the heteroatom, it will be shown. And then the formal charges are also shown. Okay, this is chapter topic 1.7, the formal charge. So what is the formal charge? The formal charge is a proper Lewis structure that state that it must have the proper formal charge. Okay, so the formal charge is equal to number of valence of the three atom minus by the number of bonding divided by 2 minus number of bonding. Okay, so this is example. You can see the example here. Resonance. Okay, two or more proper Lewis structure can be written for a compound or ion. This is simple. You can see here whether it can be written as for a compound or also as an ion. So it's known as resonance. So nitromethane can be can be drawn and can be represented by in terms of compound or in terms of ion, because it carry negative charge and positive charge. Same goes also to benzene. So you can see here what is the correct structure. It's actually both are the correct structure and neither is correct. Okay. Okay, so how you are going to draw and interpret the resonant form? This is the step-by-step guideline of drawing and interpreting resonant form. Okay, no one resonant form accurately depicted the structure of the molecule. The real structure is a composite or hybrid of all resonant form. Okay, resonant form differ only by the placement of electron, usually non-bonding electron pair or electron pair of double and triple bond, So neither position or hybridization of the atom can change. So the resonant form are not necessarily equivalent, while all resonant form contribute to the actual structure, which is in this case representing the resonant hybrid. And then some form may contribute more. Okay, all resonant form must be properly structured, including it representing the formal charges. Okay, so the actual resonant hybrid is more stable than any single resonant form. So in general, the greater number of resonant form, the more stable the resonant hybrid. So I repeat, the greater the number of resonant form, the more stable the resonant hybrid. Subtopic 1.1, Curve arrow and chemical reaction. The curve arrow convention. The curve arrow show the movement or flow of electron during bond breaking and or bond making process. You can see here double-headed arrow and single-headed arrow. Okay. The foot of the arrow indicate where the electron or the electron pair originate. So you can see here where it's being originate. If you do like this, so it's originate from here. Okay. The head of the arrow show where the electron or electron pair end up. So the head here show where the electron are going or where it end up. Okay. So the movement of a single electron can be denoted by a curved single-headed arrow, fish hook or hook. You can see here this is a fish hook or hook, fish hook or hook. The movement of an electron pair is denoted by a curved double-headed arrow. Okay, so if an electron pair move in on a new atom, another electron pair must leave, so that the atom does not exceed a full valence of its electron. There are two common, however, there are two common exceptions. The first one, when an atom already has an incomplete valence, okay, the second one, this second row or below element, the octet root must be violated. Okay, so the arrow completely dictates the living structure of the product. Okay, arrow in organic chemistry. Okay, so there is three types of arrow in organic chemistry. Basically, the first one arrow representing the reaction arrow. You have a reversible arrow looking like this. It actually representing or telling you the equilibrium arrow. If you see this type of arrow is actually representing the resonant arrow. Okay, when talking about organic chemistry, there is a reaction that involves a lot of mechanism taking place. For the mechanism arrow, it must be consist of double-headed arrow. It must have a curve here like this. can be represented by a double-headed arrow or a single-headed arrow. Subtopic 1.12 Acid and bases. The Arrhenius view. Okay, so I want you to read regarding the Arrhenius views so that you have a better understanding regarding this. So the Arrhenius view is actually regarding the acid and base. In the Arrhenius view, view acid as a substance that ionizes to give a photon H plus H carrying a positively charged when dissolved in water, whereas the base is actually a substance that ionizes to give hydroxide, okay, OH carrying the negatively charged when dissolved in water. Subtopic 1.12 Acid and base. The Bronsted-Lowry view. Acid from the Bronsted-Lowry view, he viewed acid as a photon donor, where base is the photon acceptor. So B is represented by the equation here. You can see here B acting as a base, whereas HA representing the acid. We have equilibrium arrow here. So BH is the conjugate acid and A carrying negatively charged is the conjugate base. Okay, another example is H2O combine or react together with HCl. It will produce an equilibrium arrow here to produce hydronium ion, which consists of water carrying a positively charged H2O and combine together or pair together with H, whereas the chlorine here will carry the negatively charged electron. Okay, so in dilute solution, the H2O concentration is constant, is equal to 5.5 molar and is therefore incorporated in the acid dissociation constant. Acid strength is often given by the pKa value. Okay, pKa is equal to negative log 10 Ka or the acid dissociation constant. The lower the pKa value, the stronger the acid strength. So you must remember, the lower the acid dissociation constant, the stronger the acid will be. Conjugate base of strong acid are weak base, whereas the conjugate base of weak acid are strong acid. Okay, vice versa. Okay, table 1.8 is representing the acidity constant of acid. Okay, you can see here weaker acid and stronger acid, stronger base and a weaker base. So the acid, okay, weaker acid, okay, you can see the acidity constant. Okay, you can see here becoming more and more stronger the acid once it go to the throughout the uh, throughout the uh, unit. Okay, whereas the conjugated base, you can see here is getting strong. The base is getting stronger throughout the unit. So subtopic 1.4. So what happened to pKb? Please read. Here regarding this, okay, a separate basicity constant, okay, B is not necessary because of the relationship between acid strength, okay, acid strength and the conjugate base strength. Acid-base reaction can be described as successfully using pKa value. Okay, so how structure affect acid strength? The first one, the HA bond strength, the weaker the HH bond, and the more readily it is broken, meaning that it is more acidic. Okay, So the electronegativity of an ion it will cause an effect known as inductive effect. You can see here this example of molecule that also have a pKa value. Okay, to show the type molecule, what are their pKa value. Okay, electron delocalization in the conjugate base. Okay, this is an example of electron delocalization in a conjugate base. You can see how the molecule react together with water to form the conjugate electron delocalization. Subtopic 1.16 acid base equilibrium. Okay, you can see here the reaction of weaker acid with weaker base. So in this case, water representing the weaker base. So it will produce, reversible reaction. It will produce a stronger base combined together with a stronger base. So the pKa value will be a negative 1.7, showing to you that this is the pKa value of a stronger acid. The pKa stronger acid react together with sodium hydroxide, representing the stronger base. It will produce a reversible reaction. So it produce a weaker base and also weaker acid. Weaker acid is water. Okay, you can see the pKa value is 15.7. Okay, drastically different from the pKa value of the starting reaction. So the equilibrium favor the side of weaker acid and weaker base. You must remember this rule. So a strong acid is one that is stronger than hydrogen ion. So the pKa value will be relatively around minus 1.7. So a weak acid is one that is weaker than hydrogen ion. Okay. So a strong base is one that is stronger than the OH. So you must remember lah. That strong base is one stronger than the OH, whereas the weak base is one that is weaker than the OH. Okay, remember. Weak base is weaker than OH. Strong base, okay, is greater or stronger than the OH. Subtopic 1.7 Lewis acid and Lewis bases. Okay, stated that acid is actually an electron pair acceptor, whereas the base is actually an electron pair donor. So this is how it characterizes whether the molecule is acid or base based on their proton sensitivity. Okay. Okay. Thank you all. So this topic will be continued in part 2. Okay, in my lecture in part 2. Thank you so much for your time and also listening. Okay, hopefully you have a better understanding regarding this topic. Okay, this is the chapter 1, the introduction to organic structure and bonding. Have a pleasant day ahead. Thank you so much for your time.